I'm Mark Renes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 27. We start with the quadratic polynomial n squared plus n plus 41. As it turns out, by sheer happenstance, this formula will produce a consecutive sequence of prime numbers when given integers from n equals 0 to n equals 39. When n equals 40, we finally get a composite number. We can actually go further than that. The polynomial n squared plus 79n plus 1601 produces a total of 80 primes, for n values from 0 up to 79. The problem description asks us to find the a and b values within the range specified for which n squared plus an plus b produces the longest string of primes starting at n equals 0. Once we've done that, multiply the coefficients a and b together, and you have your answer. Let's jump right in and calculate this directly. Today, we'll start drafting up a solution in Scala. We've already used Scala once before in this challenge to write up a draft. Scala is a language designed to run on the Java Virtual Machine, or JVM, and brands itself as a language supporting both functional and object-oriented paradigms equally. The first thing we'll need, as is so often the case, is a function to check whether a given number is prime. Our polynomial is quadratic, and all coefficients are bounded by 1000, which means our outputs should be in the neighborhood of a few million. That is to say, standard 32-bit integers should suffice for today's work. We've written several primality checkers in the past, but there are a couple of things I want to talk about here already. If n is less than 2, then the number is clearly not prime. Note that this also excludes negative numbers from being considered prime. The question of whether a negative number such as negative 7 is considered prime is itself an interesting one. A ring theorist would say yes, since the principal ideals generated by 7 and negative 7 are the same, and therefore the two values are indistinguishable from the perspective of ring theory. A number theorist, on the other hand, might argue that the question is ill-formed, as the notion of a prime number only makes sense for integers greater than or equal to 2. For today's purposes, we'll be erring on the side of the number theorist and removing any negative numbers from consideration for primality. If you're used to Scala 2, then the indentation-based syntax I'm using today might throw you for a bit of a loop. I'm writing in Scala 3 today, which supports a new indentation-sensitive syntax in addition to the traditional curly brace delimited syntax inspired by Java. One other thing that might be confusing here, if you're not familiar with Scala, is the final line of this function. It may look like the names until and for all are some sort of language keywords, but they're actually ordinary method calls being used as infix operators in the same way that you might use the plus sign or minus sign as infix operators. In Scala 2, any method call can be used in infix notation. In Scala 3, the rules are tightened up quite a bit, so that only symbolic operators and methods marked with the special infix keyword can be used in this way. But to maximize compatibility with Scala 2, standard library functions such as until and for all can still be used as infix in Scala 3. If we cut out all of the syntax sugar and use the Scala 2 compatible syntax, then this is the function we end up with. This is exactly equivalent to what we wrote before, just with a more traditional Java-style syntax. With all of that out of the way, let's write our main loop. We'll let a range from minus 999 to 999, and b range from minus 1000 to 1000. For loops in Scala can take multiple clauses and iterate over the Cartesian product of the iterables. Put another way, a for loop with multiple clauses can be thought of as multiple nested for loops. Inside our loop, start the input value of the polynomial at 0, and iterate until we find a non-prime value. If this streak of primes beats our current longest streak, save it and its coefficients. Then, at the end of the loop, print out the product of the two coefficients. This already solves our problem, and in about 4 seconds. But we can improve it. Let's start with the isPrime predicate. Primality checkers are ripe for memoization, since we often call this predicate with the same value multiple times for different reasons. Let's create a top-level variable called primesCache, which stores the previous primality results. Then, inside of the isPrime predicate, we first check if the value is in the cache. If so, return the cached Boolean result. If not, calculate primality, store the result in the cache, and return it. Some of you may be wondering how we're declaring a global variable here. After all, Scala is a JVM language, and Java doesn't really have global variables. Further, Java doesn't have top-level functions either, or anything outside of a class. And in fact, Scala 2 wouldn't allow this. Scala 2 follows the Java convention of requiring all functions and variables to be wrapped inside of the safe confines of a class. To make this more palatable, back in Scala 2, we could declare a special kind of object called a package object. A package object is just a regular singleton object, but other code in the same package can pretend it's defined at the top level. That is, if we define a package object, then classes defined in the same package don't need to qualify or import functions and variables defined in the package object, as those names are just implicitly imported into such scopes when needed. Scala 3 deprecates the notion of a package object and simply does the same thing for us behind the scenes without the need for a language keyword. So in Scala 3, when we write these functions and variables at the top level, they get implicitly wrapped in a singleton object with a name based on the name of our source file, and then imported automatically into any scope within the package. But as Scala programmers, we don't have to think about that very often, since the code just works as though it was defined at the top level. Next, note that we currently iterate from 2 up to and excluding n when looking for potential factors. This is very wasteful, as we've discussed before, since factors of a number always come in pairs. Every factor I of a value n is paired with the factor n over I, and these factors always sit on opposite sides of the square root of n. So if n has a non-trivial factor, then it will have a non-trivial factor less than or equal to its square root. That is, we don't need to search all the way up to n, we can simply stop at the square root of n instead, or more precisely, we can stop at the floor of the square root of n, inclusive. We'll do just that with take while, which does exactly what it sounds like. This method takes an iterable and returns a new iterable containing the longest prefix of the original, up to and excluding the point where the predicate first becomes false. Note that this is different from filtering a list. The filter method returns a sublist consisting of all of the elements for which the predicate is true, whereas the take while method returns the longest prefix for which the predicate is true. The crucial difference is that the latter short circuits, which gives us our desired performance boost. We've optimized the isPrime function, now let's talk about the main function. To do that, we need to take another look at the polynomial we're scrutinizing. We want this polynomial to produce prime numbers for as many values of n as possible, starting at n equals 0. But n equals 0 is actually quite easy to compute. If n equals 0, then the value of this polynomial is simply b. In that case, the value of the coefficient a is irrelevant. And if we want our streak of primes to have any chance of being the longest at all, then n equals 0 clearly needs to produce a prime number. That is, in order for our streak of primes to be non-trivial, b must be prime, so we can throw out any values of b which are not prime right away. Let's do just that. Instead of iterating on a first and then b, we'll iterate on b in the outer loop and a in the inner. Since b must be prime, there's no sense in trying any negative numbers or values less than 2, since we defined numbers less than 2 to be non-prime. So we can start iteration at b equals 2. Next, in between the two iteration clauses, we'll throw a guard that checks if b is prime. This effectively calls filter on the prior iterable before continuing with the remainder of the for loop. Now we only iterate over values of b which have a chance of giving us useful streaks of prime numbers. This changes our solution from big O of n squared to big O of n log n, since the prime numbers are distributed logarithmically. Now we have our solution, and this is roughly what we'll translate into our language of the week. But just as a brief tangent, let's see what this would look like when written in a more functional style. Remember that Scala is designed to support both paradigms, the imperative style we've used here and a much more functional programming style. Instead of doing the whole computation in one loop, let's first generate the candidate pairs of a and b values. So far we've been using traditional imperative for loops, which are indicated in the new Scala 3 syntax by the keyword do, and in the old style syntax by the absence of the keyword yield. An imperative for loop iterates over one or more iterables for the purposes of executing some side effects. But if we replace the word do with the word yield, we get a functional style for loop, sometimes called a comprehension. Scala's comprehensions are incredibly powerful, and they support the same semantics as an imperative for loop, including our guard clause from before. So to generate our list of candidates, loop for b from 2 to 1000, filtering out any values which are not prime, then loop for a from minus 999 to 999. For these values, yield a 2-tuple consisting of a and b. If this were part of a larger program, I might give this tuple a name in the form of a case class, just to document its purpose a bit better. But for our limited use case here, we'll use an ordinary tuple. Now we want to iterate over this candidates collection, maximizing a particular property. For given values of a and b, this property is the length of the streak of prime values produced by the polynomial, starting at n equals 0. We've already seen a function to produce the longest prefix of a sequence, which satisfies some condition. That's called the take while method. So, produce a lazy list of numbers starting at 0 and going up forever. Then take the longest prefix of that list, which produces prime numbers when plugged into our special polynomial. Next, take the length of the prefix. Finally, multiply the coefficients and print the result. And that is a functional programming-oriented solution to this Project Euler challenge. Now that we've had our fun in Scala, let's talk about the language of the week. This week, we'll be working in Ioke. Ioke is a prototype-oriented programming language, and it takes a lot of inspiration from Io, a language we've already used for this challenge. In fact, superficially, the syntax of Ioke looks a lot like Io, to the point of being almost indistinguishable to the untrained eye. But Ioke takes the prototype-oriented paradigm and the homoiconic nature of Io to its natural conclusion. As a brief reminder, the prototype-oriented paradigm also falls under the broad umbrella of object-oriented programming, but stands in stark contrast to the more common class-based approach. In a class-based language, we define classes which denote the shape of our data, and then those classes construct instances containing the actual data. In a prototype-oriented language like Io or Ioke, there's no distinction between classes and instances. We merely construct objects, and those objects might learn some of their behaviors from other parent objects. This is an example program in Io that we wrote a while ago. We started by defining 3 objects: animal, cat, and dog. The animal object is a clone of the canonical root object, and cat and dog inherit from the former in turn. Then we ask the canonical example of a cat to meow, before making our own cat and asking that one to meow as well. Crucially, even though I capitalized the first letter of the words animal, dog, and cat as though they were classes, there's no fundamental difference between those objects and the specific instance I called my cat. Now here's the same program written in Ioke. Superficially, the two are nearly identical. We clone objects using mimic rather than clone, the root object is called origin rather than object, and assignment is done with an ordinary equal sign rather than colon equals, but otherwise the two programs look basically identical. Ioke draws a lot of its inspiration from Io. Since we've already seen Io, today we'll be focusing on some of the things Ioke borrowed from other languages and added to its syntax and standard library. And let's start with the case function. Io has a rudimentary switch case statement. There's a method defined on the root object called switch, which effectively behaves like a C-style switch statement. This is an example from the official Io documentation for that method. Switch takes 0 or more arguments and groups them in pairs. The first of each pair is a discriminator. If the discriminator compares equal to the message receiver, per the double equals method in Io, then the second element is chosen as the switch clause and then evaluated. If none match and there are an odd number of arguments, the last argument is treated as the else block. Ioke, on the other hand, bases its case method on Ruby's extremely powerful case blocks. Ioke's case method takes the discrimination object as the first argument, then any number of clauses, and finally an optional else clause. The first discriminator that matches has its respective clause evaluated and the result returned. If no clause matches, the final else block is executed if it exists. So far, this sounds very similar to Io's approach, but there's one very crucial difference. Io uses the double equals operator for discrimination, while Ioke uses the triple equals operator. Not convinced? Let me explain. In Io, the operator used for switch discrimination is the same as the operator used for standard equality comparison. In Ioke, standard equality comparison is still done with the double equals, while case discrimination is done with a separate operator denoted as triple equals. This is consistent with Ruby's treatment of these two operators. If you're familiar with JavaScript, where triple equals is just a stricter form of double equals, that's not what's happening here. Triple equals is a distinct operator with its own semantics and expected behavior. In particular, whereas double equals equality is generally expected to be an equivalence relation, that is, reflexive, symmetric, and transitive, at least in spirit, triple equals equality has no such expectation. You should think of the latter operator as being more like a pattern matching operator, sort of like Raku's smart match operator. Many built-in data types in Ioke take advantage of this. Ordinary literals, like strings and numbers, simply delegate the matching operator to the standard double equals operator, so we can still use literal values as case discriminators, just like in Io. Several built-in type names, such as text and list, will also check for membership in the target's mimic chain. That is, if the name text is used as a case discriminator, then it performs what is essentially a type check, asking whether the value being discriminated is a text object or not. Similarly, regular expression objects implement the triple equals case match operator to perform a regex pattern match, so the case method can also be used to do regex matching. Ranges, written with an infix double dot, check for membership in the range. And the list goes on. Block objects, such as those defined as lambdas with the fn method, invoke themselves with one argument when used as a case discriminator. And, of course, since this is simply a method name being passed as a message, your own objects can implement their own matching behavior by simply implementing a method with the name triple equals. On top of that, there are also combinator objects that can be used. And, or, not, and so on, each accept matcher values and produce a combined matcher value with an appropriate triple equals method. For instance, the AND method takes 0 or more objects and produces a new object whose triple equals requires each of the constituent triple equals methods to succeed. In this way, we can value match against just about whatever we could dream of. This makes it incredibly easy to write methods, for example, which behave differently based on the types of the inputs, similar to function overloading in a language like Java. But value matching is only half of the game. Lots of modern programming languages support some form of pattern matching with destructuring, and Ioke is no exception. Ioke's destructuring syntax is quite powerful, for reasons you'll see in just a minute. In its simplest form, destructuring in Ioke looks similar to the same feature of Python. The left-hand side of the equal sign can have multiple variables enclosed in parentheses, and the right-hand side will be instructed to destructure itself. Specifically, in this example, a message with the name as tuple will be sent to some value. If that message produces a result which is a tuple of length 2, it's destructured successfully. If it produces anything else, an appropriate condition is signaled, which is Ioke's mechanism for error handling. The right-hand side is evaluated before any names are assigned, so this allows us to do Python's famous one-line swap trick in Ioke. If we don't care about a particular value, we can put an underscore in that slot to discard it. Further, an underscore in the last position is a special case which will ignore the tail of the resulting tuple of any length. So this example requires that some value as tuple returns a tuple of at least 2 elements. The first 2 are assigned to x and y, and the rest are silently discarded. Destructuring assignment can also be nested, so that nested lists or tuples can be matched using this syntax. But the coolest thing about Ioke's destructuring assignment is that it can be applied to basically any part of the assignment, not just to the variable name. I could try to explain, but the example in the official Ioke documentation does the feature more justice than I could. We start with a mutable list of the integers from 1 to 10 inclusive. Then we parallel assign to 3 places in that list. That is, we set the 5th value to 2, the 0th value to 3, and the 2nd value to 4. Let's zoom in on that second line and see what it desugars to. First, we have a parallel assignment to 3 places on the same named object, so we distribute the name on the left. Now we have assignment of 3 values to 3 places, so we can treat the assignments separately. Note that I'm performing them in sequence here. I could do that since the right-hand side doesn't depend on x, but in general, these assignments would happen in parallel. Now, assignment using the equal sign becomes a method call on the current ground. So each of these assignments is a call to the method equal sign on the current ground object, which you can loosely think of as being Ioke's equivalent to the current scope. Now, the equal sign method on the default ground object can do a couple of things based on what its left-hand argument looks like. In this case, the left hand looks like a method call, so we suffix an equal sign onto the end and call that method. In the end, we invoke the method called open bracket, close bracket, equal sign on x with 2 arguments. And to be clear, each step of this process is very accessible to the programmer. One of Ioke's primary design goals is to provide a powerful modifiable reflection system similar to Lisp. We could always override the equal sign method on the current ground, which could be our own object or the global ground. Or we could alter the bracket equals method on a particular object to do something else we control. By the way, Ioke treats square brackets uniformly regardless of where they appear. We can construct lists with square brackets, but this isn't a special case of anything. Square brackets appearing in the vacuum are still just a method call, and a method call without an explicit receiver is a method call on the current ground. So square brackets standing on their own will invoke the method open bracket close bracket on the current ground, and the default ground's behavior is to construct a list. Curly brackets work the same way, and the default ground defines the curly brackets method to construct a key-value dictionary of its arguments. We've seen some neat syntax sugar and some ways Ioke borrows from Ruby to make things more ergonomic. Let's move on and talk about iteration. We've worked with iterators or enumerators in various languages already, but there's one distinction we haven't really addressed. A few videos ago, we discussed C++ iterators. C++ has quite the iterator hierarchy, but at its core, the most basic type of C++ iterator supports 2 operations, incrementing and dereferencing. Java takes a similar approach, but gives the methods proper names. Specifically, Java provides a method called next, which advances the iterator and produces the next value, and a method called hasNext, which returns true if there exists a next value. Python codified the same pattern, but using exceptions. So next advances the iterator blindly, but throws a stop iteration exception if there is no next value. All of these approaches share one common detail. The iterator is a concrete object which exists within our control. We hold an iterator and decide when it advances. We refer to this model as external iteration. Oftentimes, explicitly iterating in this fashion is inconvenient and verbose, which is why most languages that are built using external iterators provide higher-level primitives to work on top of them. C++ provides the algorithm header and, more recently, the std ranges namespace to make working with iterators more convenient. Java provides the streaming API we've used in the past, and Python provides itertools. All of these APIs have the stated goal of making external iteration ergonomic to work with in practice. On the opposite extreme, consider Ruby. In Ruby, we never write explicit iterators. To make an object iterable in Ruby, we provide a method called each that knows how to apply an arbitrary block to each object of our iterable. Then, we usually include the enumerable module, which provides many helpers built on top of the each method. But the key thing is that we, as the programmer, never actually see an iterator object. We just call methods, and those methods are the fundamental tool of iteration. The each method is not built on top of an iterator API, it is the iterator API. We call this approach internal iteration. Adherents to the external iteration model provide internal iteration helpers to make their languages more ergonomic. Ruby likewise provides the opposite. We can take any object iterable with an each method and turn it into an enumerator object with an appropriate constructor. And Ruby's enumerator is as close to an external iterator as we can get in Ruby. In fact, as a convenience to the programmer, standard library each methods give you an enumerator for free if you neglect to pass a block. Ioke provides both forms of iterators. Iterable objects can provide an each method to implement internal iteration via the enumerable mixin object. But iterable objects can also provide a seek method to implement external iteration. In the latter case, the produced sequence object shall implement next and the next question mark method, which work like Java's next and hasNext, respectively. It's generally recommended to implement seek and use external iteration in Ioke when defining your own collection types. By doing so, you can use the mixin object sequenced to produce an appropriate each method for free, thereby supporting both methods of iteration while only having to write one iterator. On top of this, Ioke also steals Scala's for loop, almost word for word actually, to provide a powerful loop comprehension syntax. Ioke's for syntax, which again is just a method on the default ground object, can iterate over one or more enumerable objects, allows local assignment of variables, and can filter out values in the middle of iteration. and these calls desugar to flat map, map, and filter calls almost exactly like the equivalent syntax in Scala. Ioke also borrows a lot of neat ideas from Common Lisp that we don't have time to go into today. These include macros, the const statement, a very powerful let construct capable of dynamically rebinding any place, and even an implementation of aspect-oriented programming, allowing you to modify existing methods by augmenting what happens before, after, and around them. That last feature should sound familiar to any Common Lisp programmers listening, as it's basically the same feature as auxiliary methods from the Common Lisp object system. The bottom line is, Ioke takes prototype-oriented programming to its logical conclusion. It starts with what I/O provides, but adds a ton of great ideas from other programming languages into the mix, and the resulting language is very powerful. With all of that in mind, let's take a look at our Project Euler problem. We'll implement our more imperative solution today, so the code we write will be a fairly straightforward translation of this Scala code. Let's get started. First we'll write isPrime, and we'll write it directly on the number object so we can call it like a method. We define a top-level dictionary to store our prime numbers cache. Now, isPrime is a method of 0 arguments, since we'll get the number to test as the implicit receiver argument, self. If self is in our prime numbers dictionary, return the value at that position in the dictionary. If not, use our superpowered case matching on self to determine what to do next. If self is less than 2, then consider it non-prime. If self is exactly equal to 2, consider it prime. We need a special case here for 2 since Ioke's ranges work both up and down, so a range which starts at 2 and goes to 1 actually contains 2 values. By contrast, the same range in Scala from 2 to 1 would be empty, since ranges in Scala always try to go up unless you ask for different behavior. Finally, if x is greater than 2, produce the range of values from 2 up to self minus 1, take while less than or equal to the square root, and check whether all the values are non-factors. Store this in the caching dictionary and return it. Now we write our main loop. Start with the b iterations going from 2 to 1000. Filter out non-primes, then iterate on a. In Ioke, just like in IO, methods such as each that execute blocks will generally take the block argument name and the block itself as separate arguments, rather than taking a single lambda-like object like you might do in Python or Ruby. Inside our loops, find the length of the prime number streak. If the streak is longer than the best one we've found so far, store the coefficients in the streak length. Finally, outside the loop, print the result. And that's all there is to it. Ioke is not quite as fast as Scala, owing mostly to its nature as a dynamically typed interpreted language, so this solution takes about 30 seconds to run. But it produces a correct answer, and that solves Project Euler problem number 27 in Ioke. Tune in next time when we take a look at problem number 28 in Bufunge, the father of two-dimensional programming languages. See you guys then.